The final integration technique we are going to learn is called partial fractions. Many pre-calculus classes explain the algebra of partial fractions, and if you haven't seen it, that's totally fine, but it's completely possible that you've seen part of this before. So we're going to find something called the partial fraction decomposition for 1 over x squared minus 4x plus 3. And what that is we assume that 1 over x squared minus 4x plus 3 came from adding two other rational functions together. And perhaps if we can express this function as those two functions added, it will be easier to integrate this function. So first, start by factoring the denominator of 1 over x squared minus 4x plus 3. That's the same thing as 1 over x minus 1 times x minus 3. Now there's a theorem that is outside the scope of this course, so I'm afraid you can't ask me why, that says that this had to come from some number a over x minus 1 plus some number b over x minus 3. So a and b are constants. Now, you think, okay, to get a common denominator on the right side, I'd multiply the first fraction by x minus 3 over x minus 3, the second one by x minus 1 over x minus 1. Another way to think about that is you can take this whole equation and multiply everything by x minus 1 times x minus 3. So that x minus 1 times x minus 3 factor distributes. When it distributes to the right side of the equal sign, you just have 1. When it distributes to the a over x minus 1, you're left with a times x minus 3. When it distributes to the b over x minus 3, the x minus 3 cancels and you're left with plus b times x minus 1. Now there are two methods for figuring out the values of the a and b coefficients. So one I'll call the cover-up method, and two is a sort of gathering like terms method. And the cover-up method is the easier one, but it does not always work. So here is we'll do the gathering terms. So I'll call it gather terms. Those are my own names, so if you use them on somebody else, they might not know what you're talking about. So to gather terms, first start by distributing the a and the b, and you get 1 equals ax minus 3a plus bx minus b. And then group the x's together and take out the greatest common factor. So the x terms are ax plus bx. That's x times a plus b. And then minus 3a minus b. And what you know is this, that this side of your equation has to equal that side. A plus b is the coefficient of the x term. There is no x term on the left side, so that means that a plus b has to be 0. So had there been an x term, a plus b would have been equal to whatever the number was in front of that x. Now, the negative 3a minus b, that's your constant, and you know, since the constant on the left side is 1, that negative 3a minus b will have to equal 1. And this is a system of equations, and you can solve it using a technique called substitution. So you can say, well, I know that a equals negative b, so I can input negative b for that a. So that will be negative 3 times negative b minus b equals 1. So that is 3b minus b is 2b. Therefore b is 1/2. And now, since b is 1/2, and we know that a plus b is 0, a will have to be negative 1/2. Okay, that's not your answer, but that's the value of the coefficients. So what that tells you, I gotta give myself some more space here. That tells you that 1 over x squared minus 4x plus 3 came from taking negative 1/2 over x minus 1 and adding it to positive 1/2 over x minus 3. And if you want to check your answer, you can combine the terms on the right side and that will work. Now before we actually do the integral, I want to show you the other method that I'm going to call the cover-up method. And for this particular problem, the cover-up method is the one that I'm going to go with as the way to solve it. We'll also discuss when it doesn't work. And even if it doesn't work, you can hybrid it with the other method. So start with the 1 equals a times x minus 3 plus b times x minus 1. If you cleverly pick values of x, you can make certain terms go away so that you can find a and b easily. So, for example, if I were to plug in x equals 3, this term disappears. So if you plug in x equals 3, you get 1 equals b times 3 minus 1, which is 2, and b is 1/2. Notice that's the same thing that we had above. And one reason that's called the cover-up method is that you can just plug in x equals 3 and cover up the a minus 3 term. You also could, to get the b to go away, you plug in x equals 1, and that gives you 1 equals a times 1 minus 3, which is negative 2, and you get a equals negative 1/2, just like above. Now the kicker is that if you have an x to plug in, it has to go everywhere that there is an x. So if there's an x on the left side, it has to go there as well. Now most of the work in these problems is the algebra of figuring out those coefficients, because the integration is ridiculously easy. So what this does for us is it tells us that the integral of 1 over x squared minus 4x plus 3 dx is the same thing as negative 1/2 over x minus 1 integrated plus 1/2 over x minus 3. And both of those integrals are really, really easy to find. The first one is negative 1/2 ln absolute value x minus 1, don't forget those bars, plus 1/2 ln absolute value x minus 3. Now that answer is good enough for me. If you're checking your answer with Wolfram Alpha, it might use log rules to do some simplifying. So for example, if you write this like 1/2 ln of x minus 3 minus 1/2 ln absolute value x minus 1, one thing that might happen is those 1/2s might be pulled up and become roots. And then you might have this expressed as a ratio. If log rules are tricky, I think I should suggest Googling them, or reading an Algebra 2 textbook, but that might happen. Either answer is correct. All right, let's do another one using this cover-up method now that we know what it is. So first step is to factor the denominator. So we have x squared plus 2x minus 1 over, first you can take out an x, so that gives you x times 2x squared plus 3x minus 2. And so this is going to be 2x and x. And let's think, multiplies to make negative 2. I think minus 1 plus 2 works. You have to double check that, but I'm positive. 2x squared plus 4x minus x makes 3x. Okay, and that will equal, so then we have 3 linear terms in the bottom. A over x plus some constant b over 2x minus 1 plus some constant c over x plus 2. And when you have a product of distinct linear factors, meaning the factors are basically like lines, so mx plus b, and they are all different, that cover-up method will always work. So now multiply by the denominator, and you get x squared plus 2x minus 1 equals a times, now that factor won't have the x, but it will have the 2x minus 1, and it will have the x plus 2. The b part will have the x, and it will also have the x plus 2. And the c part will have x and 2x minus 1. So just remember that what I did there was multiplied by the denominator and distributed and canceled. I'm just not going to write that step because it is so much writing. Now plug in clever values. So if we want to find a, we need to make the other terms go away. And to make this term and this term go away simultaneously, you have to plug in x equals 0. So when you plug in x equals 0, the right side of the equation becomes -1. The left side is a times -1 times 2. And I believe that implies that a is equal to positive 1/2. Okay, next let's try to make everybody but the b go away. So that means I'm looking at trying to kill the 2x minus 1 factor and the 2x minus 1 factor. And to make that 0, you have to plug in x equals 1/2. Okay, 1/2 squared is a quarter. So a quarter, 2 times 1/2 is 1, so plus 1 minus 1. Equals, the a factor's gone, the c factor's gone, we have b times 1/2 times 1/2 plus 2. So on the left side we have a quarter, on the right side we have b times 1/2 times 1 plus 2 is 5/2. So that's 1/4 equals b times 5/4, which implies that 1 equals 5b, which implies that b is 1/5. Okay, so we got a, we got b, now we need to find c. So now we need to make the a and b term cancel, and to do that we need to plug in x equals -2. So doing so, we have 4 minus 1 equals c times -2 times -4 minus 1. So on the right side it appears we just have -1. On the left side we have positive 10c. And so we find that c is equal to -1/10. And like I said, most of the work is in figuring out the value of these numbers. The integration, once you get them, is not very hard. So now we found our numbers, we can actually find our integral. So we know that the antiderivative of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x dx, that's equal to the integral of a over x, so 1/2 over x, plus b over 2x minus 1, so plus 1/5 over 2x minus 1, and then plus -1/10 over x plus 2. And now integrate that term by term. So first we'll have 1/2 natural log absolute value of x. Now the next tricky bit, 1/5 ln absolute value 2x minus 1. And because you had 2x minus 1 there, you're going to need to have a times 1/2 to compensate, just like when we integrated like sine of 2x or something. And then minus 1/10 ln absolute value x plus 2 plus c. And if you're faster than me, you can multiply that 1/5 and 1/2 right away. I'll have to rewrite this because I'm not done. 1/2 ln absolute value of x plus 1/10 ln absolute value 2x minus 1 minus 1/10 ln absolute value x plus 2 plus c. And I apologize for the tedium. As a result, you don't have that many homework problems, but they do all take quite a while. Now, one thing that I glossed over a little bit that I have to say is that this partial fraction technique only works if the degree of your numerator, that theorem only applies if the degree of the numerator is less than the degree of the denominator. So if the degree of the numerator is bigger than or equal to the degree of the denominator, you have to do something called polynomial long division. And everyone's experience with this is a bit different. I personally never saw this before I got to a calculus class. I must have been absent that day. So if you do not know what this is, you're going to have to look up polynomial long division. And you'll be able to find explanations on that online, but it officially is like Algebra 2 material, so you should have seen it. If you haven't, you've got to look something up to remind yourself. So we're going to divide x squared plus 3x plus 2 into 3x squared plus 6x plus 2. It helps me to think about numbers. So for example, if I say, 7 over 2, that's the same thing as 2 goes into 7, just like this. So we're going to have the same thing. The x squared plus 3x plus 2 is going to go into 3x squared plus 6x plus 2. And what you think about is that what do you multiply the x squared by to make it match this 3x squared? And the answer is 3. It's a constant, so it goes over the other constant, the 2. Then that 3 multiplies by the entire polynomial, 3x squared plus 9x plus 6, and you take it away. And the parentheses that I put right there are the thing that mess students up the most frequently. And the reason you only look at the first term is you just kind of cancel these things term by term. So just you worry the biggest term first and then go on to the next. So 3x squared minus 3x squared means no x squared. Then you have 6x minus 9x. That's negative 3x. And then you have 2 minus 6 is negative 4. And if you think about the world of numbers, you stop when this thing is less than your divisor. In the world of polynomials, you stop when the degree of this is smaller than the degree of the thing you're dividing in. So at this point in time, x squared plus 3x plus 2 goes into 3x squared plus 6x plus 2 3 times with a remainder of negative 3x minus 4. That's weird, but it is. And so what we have now is that our original thing is equal to 3 plus. That is our 3x squared plus 6x plus 2 over x squared plus 3x plus 2 is equal to 3 plus negative 3x minus 4 over x squared plus 3x plus 2. And once you've done this, you do partial fraction decomposition on that second piece before you anti-differentiate. So let's do that. And the good thing is the cover-up method works on that one, so we're good to go. So negative 3x minus 4, denominator factors into x plus 1, x plus 2. So that had to come from a over x plus 1 plus b over x plus 2, which gives us negative 3x minus 4 equals a times x plus 2 plus b x plus 1. And now input clever things. To make the b go away, we're going to input negative 1. That gives us 3 minus 4 equals a times negative 1 plus 2. So I believe that tells us that a equals negative 1. And for b, you plug in x equals -2. That tells us that 6 minus 4 equals b times -2 plus 1, which tells us that 2 equals -b, therefore b is -2. And after all that holy moly stuff, you have that your original integral, so the integral of 3x squared plus 6x plus 2 over x squared plus 3x plus 2 dx, that's equal to the integral of 3 plus -1 over x plus 1 plus -2 over x plus 2. And if you want to check and see that you're right, not that you have the energy or time, you could get a common denominator and add together the 3, -1 over x plus 1, -2 over x plus 2. And now anti-differentiate, we've got 3x, negative natural log absolute value x plus 1, minus twice natural log absolute value x plus 2, plus c. So just keep in mind that you have to apply this technique whenever the power of the numerator is bigger than or equal to the denominators. Next, we are going to find a partial fraction decomposition of a fraction in which it has the denominator that's a product of linear factors, but some of them are repeated. So what I mean by that is, notice here that instead of just being x plus 1, it's x plus 1 squared. That's called a repeated factor. So that theorem that we can't really prove to you says that when you break this down, where x squared plus x plus 1 over x plus 2 times x plus 1 squared, where that had to come from is some number a over x plus 2 plus some number b over x plus 1, and then plus some number c over x plus 1 squared. Okay. Now we do the same trick as before. We multiply by the denominator of the left side, and we end up with x squared plus x plus 1 equals a times x plus 1, the quantity squared, plus b times x plus 2 and a singular x plus 1, and then plus c times x plus 2. And now let's try to apply that plugging numbers in method and see what the problem is. So, for example, you can plug in -1. When you do that, you get 1 minus 1 plus 1. The a term goes away, the b term goes away, and you get c times -1. So that's going to be 1 equals -c. This should be +1. So therefore c is equal to 1. Easy enough. And you think, okay, well, I'm in business. Now I can plug in -2. When I input -2, I get 4 minus 2 plus 1 equals, well, -2 plus 1 is -1. Squared makes 1, so that's just a. And the other terms go away, so that gives us 3 equals a. And you're so happy because you found a and you found c. All you gotta do is find b now. But the problem is that plugging in -1 makes both this term and this term go away, and plugging in 2 makes this term and this term go away. There's no number to plug in that will make the b stay and everything else be present. So at that point in time, you have to use the harder method of grouping terms, and there's no way around it as far as I can tell. If you come up with one, let me know. So you have x squared plus x plus 1 equals a, expand out the x plus 1 squared, x squared plus 2x plus 1 plus b times x squared plus 3x plus 2, and then plus c x plus 2. And it helps to be a little bit fast to save yourself some writing to figure out who's who. So for example, what I mean by that is that I'm going to have these x squareds, and I'll have ax squared plus bx squared, so that's x squared times a plus b. Now the x's come from this term, and this term. So we have the x factored out, and then the constants there will be 2a plus 3b plus c. You could think first you distribute the a, the b, and the c, and then you group them into groups that have x squared, x's, and just constants. You take out the x squareds, take out the x's. And now for the constants. So for the constants, we're going to have this 1, this 2, and that 2, and that's going to be a plus 2b plus c. And from there you can tell that this a plus b has to equal 1. 2a plus 3b plus c has to equal 1 as well, because there's a 1 in front of the x. And a plus 2b plus c also must equal 1. Now because you've already found the value of 2 of those constants, you don't actually need every single one of those equations. The first one is sufficient. You know a plus b is 1. You know that a is 3. 3 plus b equals 1, and therefore b is equal to -2. So it actually, in that case, is best to kind of combine the methods, because solving the system that results here is pretty long and tedious. Whew! So now that we finally know a, b, and c, we can actually do our integral. So the integral of x squared plus x plus 1 over x plus 2 times x plus 1 squared dx will equal, so in this case we had a was over x plus 2, so 3 over x plus 2. B was over x plus 1, so that'll be plus -2 over x plus 1, and finally plus 1 over x plus 1 squared. Now at this stage, don't make the mistake that a lot of Calculus 2 students make. They think that whenever something's in the denominator, it has to, by default, somehow integrate to ln absolute value of x. That's only true if the thing in your denominator is like expression to the power of 1. This last one is a bit different. So the antiderivative of 3 over x plus 2 is 3 ln absolute value x plus 2. Next we have -2 ln absolute value x plus 1. And the last one, that's x plus 1 to the -2nd. So that antidifferentiates to x plus 1 to the -1st over -1 using the reverse power rule. You should probably simplify that last thing just a tad. And we have 3 ln absolute value x plus 2 minus 2 ln absolute value x plus 1 minus 1 over x plus 1 plus c. And I think by now you should notice that most of the work we do here in figuring out the a, b, and c, which is just algebra, and the integration is often not very challenging. Now next, we could have a case where the denominator is a product of distinct linear and irreducible or unfactorable quadratic factors. So here is an example of that. This denominator factors into x times x squared plus 4. And x squared plus 4 is a quadratic, meaning it has a degree of 2 that does not factor. And so that same theorem that I'm afraid I really can't prove to you, but I can tell you how it works, says that expressions of this form have the following decomposition. They are a over x, so that's just a linear term, and the thing above the quadratic must be a linear, so plus bx plus c over x squared plus 4. And you can think that above the x is the polynomial that has 1 degree less. This has degree 1, that has degree 0. Above this polynomial that's x squared, that has degree 2, this thing has degree 1. So that's the breakdown. So now multiply by the denominator of the left side, and we'll have 2x squared minus x plus 4 equals a times x squared plus 4 plus bx plus c, the whole quantity, times x. This is another instance in which the cover-up method can be used to partially solve, but not completely solve. So we can start it that way, like if you plug in x equals 0, that will kill off one of the factors. You get 4 equals 4a, and you know that a is 1, and any information is helpful, so that's great. Now that's all because there's nothing you can plug into x squared plus 4 to make it 0. That expression is never 0. The smallest it is 4. So group terms, we got 2x squared minus x plus 4 equals, now let's think about where the x squareds are going to come from. Maybe from here and from here once that x has distributed. So we're going to have x squared times a plus b. And then next we're just going to have the only x term is going to be cx. And the only constant term will be that last 4a, which comes from here. And actually now it's not so bad. So for example, a plus b, that's the coefficient of x squared, that must be 2. A plus b must equal 2. And because you know a is 1, 1 plus b has to equal 2, so b has to equal 1 as well. And then c, that's the coefficient of x. Well, c has to be -1. No solving there, you know what c is. So you have a, you have b, you have c, all the information you need. Now let's plug those in and use them to find the integral. So the original integral of 2x squared minus x plus 4 over x times x squared plus 4 is equal to the integral of 1 over x plus x minus 1 over x squared plus 4. Okay, the first integral is easy. The second one, you're really hoping you could use substitution, but that's not going to work because x squared plus 4's derivative is 2x, and you have x minus 1 up top. So what you have to do is break that into two fractions as follows. Make it into x over x squared plus 4 minus 1 over x squared plus 4. And now you can integrate term by term, and it shouldn't be horrible. The antiderivative of 1 over x is ln absolute value of x. This middle term is actually going to be 1/2 ln absolute value x squared plus 4. If you wanted to work that out to convince yourself that's what that is, you could let u equal x squared plus 4 and do a substitution. And then the last term, that's that arctan formula that maybe your Calculus 1 book didn't go over super well, but we went over recently. So this would be -1/2 tan inverse x over 2. And that tends to happen a fair amount with irreducible quadratic, so it's probably good to sort of be familiar with that formula. As with much other stuff we've done, various techniques can be combined to make things into integration in this particular manner. And so for this problem, what the best thing to do is to do a substitution, and it's always tricky to choose what to substitute for. In this one, what you choose to substitute is root x plus 1. And so then du is 1/2 the quantity x plus 1 to the negative 1/2 dx, or 2 roots of x plus 1 du equals dx. And this root x plus 1 is just u, so that's 2u du equals dx. So dx is replaced by 2u du. The root in the numerator is replaced by u, and the question is, what about the denominator? Well, to do that, you take the substitution and solve it for x. So u squared equals x plus 1, and u squared minus 1 equals x. I know this is tricky, probably going to be more a homework question than a test question. So integral of u times 2u du over u squared minus 1, which is the same thing as the integral of 2u squared over u squared minus 1. And you could choose to pull that 2 out at this stage, but you don't have to. I chose not to, so your work will look different than mine if you do pull it out, so probably for now let's just not, so we match. Okay, now partial fraction decomposition has a couple sort of complicated bits. Like the first thing is you've got to do long division. So I'm so sorry, but step 2 after substitution is to do long div. So we're dividing u squared minus 1 into 2u squared, and that will be 2. So minus 2u squared minus 2. The 2u squareds cancel, we're left with positive 2. So now this can become the integral of positive 2 plus 2 over u squared minus 1 du. So there's first step. Second step, actually. And now the third step is to take this part and break it up using the partial fraction decomposition. Thankfully, the cover-up method will work. So 2 over u minus 1, u plus 1 will equal 2 over a over u minus 1 plus b over u plus 1. So 2 equals a times u plus 1 plus b times u minus 1. And now input clever u's. If you input u equals 1, you get 2 equals 2a, therefore a is 1. And if you input u equals negative 1, you get 2 equals negative 2b, and therefore b is negative 1. Whew, man. So we now have integral 2 plus 1 over u minus 1 plus negative 1 over u plus 1. You are very tired. So we get 2u plus ln absolute value u minus 1 minus ln absolute value u plus 1 plus c. And then final answer is to plug your u back in. So 2 root x plus 1 plus ln absolute value root x plus 1 minus 1 plus ln absolute value root x plus 1 and then plus c. Holy moly. And on that one, I'll totally concede that the substitution to make is completely not obvious. I haven't thought about if it's possible to make u equal x plus 1 in the root sign and kind of go from there, but I suspect that that does not work out. So same idea, substitution. The thing to notice here is that e to the 2x is actually e to the x squared. So that's something that not all students understand. So just note that. And this substitution is much, much, much easier. Just let u equal e to the x. Then du is e to the x dx. So that 1 e to the x in the numerator gets replaced by du. And our integral becomes the integral of 1 du over u minus 2 times u squared plus 1. So it's another example of one of those irreducible quadratics. The u squared minus 1 is u squared plus 1 is an irreducible quadratic. Okay. All right, let's break this down into its partial fraction decomposition. So we have 1 over u minus 2 times u squared plus 1 equals a over u minus 2 plus bu plus c over u squared plus 1. Multiplying by the denominator of the left side, we have 1 equals a times u squared plus 1 plus bu plus c times u minus 2. Now input u equals 2, and we get 1 equals 5a. So we know that a is a fifth. Okay, now doing some more, we're going to have to group terms. So you have 1 equals, let's just multiply this out, au squared plus a plus bu squared minus 2bu plus cu minus 2c. And in grouping terms, we'll have u squared a plus b plus u times negative 2b plus c, and the constants are a minus 2c. Now, since there is no u squared on the left side, you know that a plus b has to equal 0. And if a is 1/5, you know that b has to equal negative 1/5. Now, negative 2b plus c is also equal to 0 because there is no u term on the left side. And so that's going to give you 2/5 plus c equals 0. So c is negative 2/5. And the three constants you had were a, b, and c, so you're done finding them. All right, so now this integral of 1 over u minus 2 u squared plus 1 du is equal to the integral of a over u minus 2, so 1/5 over u minus 2 plus negative 1/5 u minus 2/5 over x squared, u squared plus 1. All right, and just like the previous one that we had that was quadratic, you got to break it into two pieces. So we have 1/5 the integral 1 over u minus 2 du minus a fifth integral u over u squared plus 1 minus 2/5 integral 1 over u squared plus 1. So the first antiderivative is 1/5 ln absolute value u minus 2 minus a fifth ln absolute value x squared u squared plus 1. I keep doing that. U squared plus 1. And then times a half to compensate. And then this last one is just arctan, minus 2/5 tan inverse of u plus c. And it's really easy to forget that you actually made a substitution way back in the beginning, like 6 minutes ago, so go ahead and plug that in. 1/5 ln absolute value e to the x minus 2 minus 1/10 ln absolute value e to the 2x plus 1, and then minus 2/5 tan inverse e to the x plus c. Holy moly. The fourth and hardest, most tedious case is when your denominator contains an repeated irreducible quadratic factor. So say something like x squared plus 4, the quantity squared. Or if you really wanted to be like super evil and take a couple pages to do a problem, cubed. So we won't do that. So this one we're mostly going to set it up. I'll tell you how to solve it, but it's just long. So the partial fraction decomposition is this. 5x to the 4th plus 7x squared plus x plus 2 over x times x squared plus 1 squared. The breakdown is a over x plus bx plus c over 1x squared plus 1, and then plus another linear factor, dx plus e over x squared plus 1, the quantity squared. And you're like, holy moly, this is going to be horrible. It's going to be a little painful, so you can do this. So multiply by that denominator on the left. Now think with the a, all that's left is the x squared plus 1 squared. With the bx plus c, we're left with a singular x squared plus 1 and also an x. And with the dx plus e, we're left with just that thing times x. Okay, great. And I think for this one, it probably is just easiest to say like group stuff. You can technically plug in x equals 0 and that will give you the value of a, but there's just so much more to find. You're gonna have to eventually do this. We should just get it over with. I'm not gonna rewrite the left side because it just takes so much space. So this will be a times x to the 4th plus 2x squared plus 1 plus, here we go, bx cubed plus bx cubed plus bx plus cx squared plus c, and don't forget that that's all still multiplied by x. I almost did, that's why I paused for a second there. And then lastly, plus dx squared plus ex. Okay, now distribute that x, and we'll have ax to the 4th plus 2ax squared plus a plus bx to the 4th plus bx squared plus cx cubed plus cx plus dx squared plus ex. And now color coding is super helpful, so I'm going to go in Roy G. Biv order. Red with the 4ths. This 4th, that 4th. So x to the 4th times a plus b. Next, let's do the cubes. So red, orange. The only cube to me appears to be the cx cubed. So plus cx cubed. We're going to skip yellow because yellow is not visible. Green. Okay, that should have been cubed. That would have been disastrous. Cubed. Okay, green for the squares. So here's a square, there's a square, there's a square. So plus x squared, 2a plus b plus d and then the x's, cx and ex, so plus x times c plus e. And then lastly, plus a on the end. That's the only constant. Woo! And there's the rainbow. Great. Now going term by term, a plus b has to equal 5. Okay, cx cubed. Well, then c has to be 0 because there are no x cubes. So that one's done. Let's box it so we know we have it. 2a plus b plus d has to equal 7. C plus e has to equal 1. And a must be 2. The good thing about these long ones is a couple of the constants seem to sort of come out right away. All right, now knowing c is 0, we can plug that in right here, and e will have to equal 1. So there we got 3. We know a is 2, so 2 plus b equals 5, and therefore b is equal to 3. And the only thing left to solve for is d. So 2a, so that'd be 4 plus 3 plus d equals 7. Looks like this case d is also 0. Now to do the integration, I'm going to call this thing equal to I. I don't really want to rewrite it. And you can use that for any homework problem that you have. So now I will equal a over x, so 2 over x. Now bx plus c, so that's just going to be 3x because c is 0. And then dx plus e will be 1 over x squared plus 1, the quantity squared. And the first two parts of that integrand are not super bad. So 2 ln absolute value x for the first one, plus 3 over 2 ln absolute value x squared plus 1. And I'm not going to work out the last one right exactly here on purpose because it's actually quite tricky. So it took me a while to figure this out, but this last one, and you can do this on your own if you care, how you have to figure this last one out by using a trig sub. If you let x equal tan theta, and you have dx is secant squared theta, d theta, that works out, that integrates, it's just fine. I won't give you anything this tricky. My main point was just to show you what the partial fraction decomposition was like for fractions that are this complicated.